Hi, I'm Darsh, and I'm presenting on a computational framework for patient-specific vascular modeling. Me and my collaborators are looking at a disease called chronic thromboembolic pulmonary hypertension, or CTEPH. CTEPH occurs when patients have a mean pulmonary arterial pressure more than 20 millimeters of mercury, and it's caused by blood clots in pulmonary arteries. CTEPH is lethal since it causes right heart failure in patients, and currently surgeons can only remove 3 blood clots at a time, but there's no way to know which blood clots will have the best impact on patient outcomes. So we created a computational framework to find optimal patient-specific treatment of CTEPH. First, we started off by looking at patient data of a healthy control subject. Using CT scans of their chest and a software called 3D Slicer, we created a 3D representation of the pulmonary arteries. Then we used the vascular modeling toolkit to find center lines through the 3D geometry, and center lines contain data on each vessel's radius and length, as well as how they're connected to each other. However, both 3D Slicer and VMTK have their own issues. The image segmentation process is a long and semi-automatic process, meaning that there could be differences in segmentation of the same data done by different users. So we had one member of our team create 5 segmentations of the same control data and verified it with radiologists at Duke Medical Center. VMTK also has an issue where it places junctions of vessel too early into the parent vessel, which creates inaccurate length and radius values for each vessel. Thus, we use change points to create a junction adjustment and radius detection algorithm, both to find physiologically accurate length and radii values. Simply put, change points occur in a dataset when the slope of the data leading up to a point is very different from the slope of the data after the point. In our algorithm, we use up to 3 change points per vessel to prevent overfitting of the data. Pictured here is the radius data extracted from VMTK for a vessel with a change point found near the end of the vessel. And we find the representative region based on the slope between change points that are next to each other, and the flattest slope is corresponding to the representative region of the vessel. Moving on to the junction adjustment algorithm, this is used to find the physiologically accurate length value for each vessel. So we look at nodes along sister vessels, and we have a distance epsilon determined by the length of the parent vessel. If the distance between the sister nodes is less than epsilon, then those nodes are actually believed to be part of the parent. So we find the midpoint between the 2 nodes and add that to the parent. We continue doing this until the distance between sister nodes is more than epsilon, and that's when we stop extending the parent and connect it to its daughters. So that gives us a physiologically accurate length value for each vessel, and it's pictured in the right in the junction adjustment section. Our radius detection algorithm uses those change points in the representative region found by it, and we have 8 different cases based on how big the representative region is, as well as where it's located along the vessel. Our radius detection algorithm will give us 1 radius value as well as a standard deviation for each vessel, based on the values in the representative region. So now we'll have 1 radius value and 1 length value for our simulations, which is exactly what we need. We want to make sure it's still physiologically accurate. So we have some assumptions. We know that the radius of the parent needs to be bigger than each of its daughters' radii values. And also the cross-sectional area of the parent needs to be less than the sum of the cross-sectional areas of the daughters. Our algorithms actually obey these assumptions more than 99% of the time. But here I have pictured a terminal or an erroneous vessel. And when this happens, we actually chop off the erroneous vessel and its sister and replace it with a structured tree using those alpha beta values to extend it past. We actually add the structured tree to each terminal vessel as well, just to make sure that we can extend our networks past the limits of CT scan resolution. So now we have accurate length and radius values that are physiologically accurate as well, so we can do fluid dynamic simulations. We solve nonlinear 1D Navier-Stokes equations using the 2-step Lax-Wendroff method to find pressure and flow values for each vessel, depending on the radius and length of each vessel. Based on all of this data, we can do patient-specific hemodynamic simulations. So we did simulations in all 5 of those networks generated from the healthy control data, but we actually at first found that they varied a lot depending on how big the networks were. Because VMTK isn't the most accurate software, it doesn't always detect the same amount of vessels for each segmentation, even though it's from the same data set. So we actually ended up pruning all the networks down to 167 vessels, which is pictured on the 2 left graphs, where the top one represents the pressure values before and after pruning, and the bottom one represents the flow values before and after pruning. We saw that after pruning them down to the same size, they're actually physiologically accurate. We also decided to sample from a normal distribution for our radii values in the simulations, and we did 1,000 simulations based on this. The dark blue line represents the radius value simulations with the radius value found from our radius detection algorithm, and the gray lines are from the normal distribution. We found that doing varying radii values was actually really important in terms of having physiologically accurate pressure and flow, but our algorithms actually created physiologically accurate pressure and flow simulations. Since the summer, we've been working with disease patients and looking at their data and doing simulations with that as well. Thanks for listening, and see you at Discover.